Welcome back, and thanks for taking that preconception quiz. We will look at those and also see how your ideas change as the quarter progresses. But one of the reasons I didn't want you to go out on the internet to do this is I really wanted to get your preconceived ideas, and I also wanted to make sure that you weren't affected by something called greenwashing. So check out these cartoons. And hopefully what you see they're hinting at is that you can paint a green picture on top of anything. And in fact, if you were to look at the concrete industry, they're going to tell you that concrete is great. It's a great thermal mass for helping you offset temperatures throughout the day in passive cooling and heating. It's made of local materials. It's durable. You can actually recycle it and use the crushed concrete as aggregate in new concrete. So it's really, really green. But what they don't tell you is somewhere between 5 and 8%, depending on the study, of all worldwide CO2 production comes from making Portland cement each year. And we'll talk about this more on Friday, but basically 50% of that is just in the production process, and 50% of that CO2 is actually released from the materials that are used in the ingredients. And even though we're doing a better job in industrialized nations of trapping that CO2, the demand for concrete is increasing exponentially, and so we can't keep up. Now, the steel industry likes to say you can recycle with steel, and it's all recycled material, so it's really, really green. What they don't tell you is that actually not all recycled members, or not all steel members, are 100% recycled material. Some are less than 40% recycled material, and the amount of energy that goes into creating, and water, to creating steel is 30 times as high as steel or concrete or timber. So you say, fine, let's stick with timber, right? This is renewable. You can just grow it. It's great. And the timber industry actually will brag that forest coverage in the U.S. hasn't changed in 100 years. They don't tell you that approximately 40% of all construction lumber, not including hardwoods used for cabinets, flooring, about 40% of just the construction lumber is imported. So other people's forests are changing. So look, I mean, the idea is basically that nothing is perfect, but we do have to have some criteria. So one of the criteria that we have to look at is its actual structural criteria. If we're going to use it as a building material, how does it function? And so one of the critical things for us is obviously its structural function. What's its strength? How well it will handle the loads? And in handling the loads, how stiff or flexible in it? How much deformation are we going to expect out of this material? We also want it to be durable, so weathering, insects, mold, everything. And then of course resist fire, because that's just a fact of life in buildings that fire can happen. Now in addition, it's really important that we look at how easy it is to build with the material, but also how easy it is to modify, because buildings change use, owner, during their lifetime, and if the building has to be torn down because it can't be modified to accept the new usage, then that just creates a lot of waste. So if we can modify it, that keeps it a little greener. And then finally, the structural material has to be something people can build with and would build with. It has to be acceptable. And so not only is that easy to deal with spatially, does it easily accept plumbing and electrical, or all the HVAC, the heating, ventilation, and cooling, but there's also that timing sequence, the temporal. How long does it take the material to set up so that you can do other construction stuff around it? Is it easy to get the other trades in and out? Because if that doesn't work, it's not going to be accepted by the trades. And finally, we do also want it to be good as thermal insulator so that the building during its lifetime uses less energy. And then of course, it has to meet all the other sustainability criteria we already talked about in the first half of this lesson. So those would be the criteria in your Wikipedia pages and in your report that you're looking at for these materials, is both the structural and these sustainable criteria. And so right now, I just want to show you a couple examples of alternative sustainable building materials. And Adobe is one I'm going to talk about. You know, more than 33% of the world lives in Adobe structures. In fact, I think 33% of new construction is Adobe in other parts of the world, and even more live in older earthen homes. Adobe is just clay, straw, and sand. And that's really all it is. Occasionally you'll have a small percent of cement, 5 to 8%. These are formed in actual molds so that you get these perfect size blocks, and they're either sun-dried, which uses no energy, or they are kiln drying, which does use energy. And you can see in the picture behind the gentleman that they are stacked to form a house. That house actually has a good footprint on it where you have concrete coming up so that it's protected from weathering, but then those blocks are not protected. Normally what you would see, this is a historic New Mexico adobe, you would have a adobe plaster on the outside that would need maintenance regularly every few years because that's sort of the sacrificial layer that weathers. Or more modern adobe construction, that's going to have a stucco adobe on the outside that is cement based, so it's more durable. Bamboo is an amazing building material. It's very, very strong in tension and compression. Its really only challenge is it being organic like wood, so it has variability, and it's challenging to connect like wood. But the advantage of bamboo is that it grows very, very quickly. It's very renewable, and it's a grass, so you can cut it down. So you literally can harvest structural bamboo every 4 years. And these are some traditional bamboo buildings with typical bamboo connection techniques. But you can also have some more beautiful modern looking buildings. I love that building. And you can make plywood out of bamboo and then create laminated beams. So this whole building, the trusses, everything here is made up of laminated plywood. And in fact, our Santa Clara students in the 2013 Solar Decathlon House used this same plywood as the web for a bamboo built-up I-joist, and then solid calm bamboo out of Vietnam. It's a small bamboo as the flange material. And you can't talk about bamboo without looking at the super cool mountain bikes out of Santa Cruz. They're not cheap. There's also earth, rammed earth. This is a beautiful material, as we can see here. You can layer your different layers of earth to give you more color. It can be a very modern looking structure, so they're quite beautiful. I'll show you that again. Sorry, went a little fast. And the way rammed earth is formed is you do create a framework. Sometimes it's reinforced plywood or steel plates that get reused, and you then fill it with your mixture, which is going to be sand, clay, gravel, and actually cement, not concrete. This image I got off a diagram should say cement. And then basically using pneumatic ram to shove it down into place and really compact it. And this is legal in the state of California to build with. You have to have cement in your mix, and those of you in the lab will complete the rammed earth challenge and design your own mixes, and we'll see how strong you can get. Code requires a whopping 300 psi. Cob is another earthen material, and it's beautiful. It's hand formed, so it's not like adobe where it's bricks. You can do a more traditional like the lower picture, or go very Hobbit like the upper picture. The interiors tend to be very organic, and those curved shapes and organics actually help the overall structure be pretty good for seismic resistant. Not necessarily the material itself, but the overall structure with all of its curved shapes and supports just give paths for the earthquake load. Cob, like adobe, is clay, sand, and straw. You don't add cement to it. It's mixed, and while wet, still formed into what they call bricks, but they're just clumps of material that you can see in the upper picture up in the front. Those clumps are then carried to the job site and just packed into shape on the house. Then say you want to put in a window like this gentleman, you get a level surface, you set it in, and he's just packing now loose cob all around the window to level it and to remove any voids. You can also build out of straw, and so the little pigs were right. And there's two ways to build out of straw bale. The first is post and beam infill. This is something that's, say, legal in New Mexico and common there and in Colorado. So the post and beam, the actual loads are all carried by wood, and then you use the straw bale as infill for insulation. But there's also something called Nebraska style, which is a lower picture, where the straw bale is the load-bearing element. This is Nebraska style because it was invented in Nebraska in the, well, at least in the United States. I'm not sure worldwide. But in the early 1900s, in the prairies, you didn't have trees, so when the early settlers came, they didn't have a way to build structures, so they just used straw bale. And some of these structures, there's a church and some houses, almost 100 years old, they're still there. The only reason they didn't continue to build this way is the Industrial Revolution. These were people who immigrated from the east. They were used to building with the forest wood from there, and once the train started going by that carrying lumber, they didn't need to use their local resource, and it's kind of a shame. These houses end up with wire mesh that's put on the faces to create a sort of sandwich panel of stucco and straw, and then a stucco material is put on. And we're actually really interested about the longevity of that wire mesh, because anytime you have, whether it's a lime plaster, a cement-based plaster, the pH levels in that plaster, if they start to get too low, which occurs during carbonation of that material reabsorbing carbon that was burned off initially during the formation of the lime or the cement, it can lower the pH, which can cause corrosion. So we want to look at that in the lab this and we'll talk about those pH levels in class this quarter. Now, with any alternative sustainable material, one of the things that's really, really important to us is that we really understand its behavior so that we can design things appropriately so that they're safe, because nobody wants this type of damage. And you could argue that this occurred simply because it's an adobe house and this is what happens when you build out of adobe, but we know ways to reinforce adobe, and the full structural analysis, that's going to be saved for the 215 class, which I hope that you will take in the spring, which builds off of this. But we need to understand the properties. We need to know, will the wire mesh corrode? What are the physical properties that would keep things strong? How do things handle for certain connections? Because even building with modern materials, this is damage after the Haiti earthquake, and that was all concrete and rebar, but it was built wrong. So just because you build with modern materials doesn't mean it's built safely, and that's our goal, is to understand these alternative materials so that we can build safely with them. And so now I want to get an idea of how appropriate you think these alternative materials are, and consider our structural criteria and our sustainability criteria, and think about the pros and cons, especially for like the cob, adobe, straw bale, bamboo that we just saw. And so you have a second preconception quiz, so please go ahead and go out and take those. Again, it's not worth points if you're right or wrong, it's just worth points if you've done it. This is to get an idea of where you stand today. So that's the end of this portion of the lesson. You do have the preconception quiz, and then if you continue down the module, there's some additional steps for you to take, especially that mechanics review. So I'll see you again for lesson 2, which would be Friday, and those of you in the lab, there's material for you out on the lab, and then I'll see you in person next Wednesday in class. Thanks a lot.